Hello, members. We are going to summarize something about skewness and kurtosis. And we say the skewness and kurtosis fall under the area of statistics where we do measure of shape of a probability distribution or any other distribution of data. So skewness is the measure of asymmetry of the probability distribution, and kurtosis is the measure of tailoredness of the probability distribution. As we go along with this discussion, we shall understand better what these two mean. So in statistics, skewness refers to the asymmetry of the distribution of data values, and when data is not symmetrically distributed, it can either be left skewed or right skewed. So when I look at these three graphs, I see that I have a normal distribution where skewness is equal to 0, that is in a normal distribution, or the distribution of the data points or data values reduces to normal distribution when skewness is equal to 0. Then it is having left skewness when you have a tail. The tail is longer on the left. So you'll find that your mean, medium, mode are in this way, and mean is less than medium is less than mode. So for a right skewness, or where we have a right a distribution skewed to the right, that is when the tail of the distribution is moving towards the right. So here the mean is greater than mode. So mean is greater than median is greater than mode. Now, in the details, we can say that left skewed distribution has a negative skewness, and the shape of it, we have already said that the tail on the left is longer or fatter than the one on the right side. And mean is less than median is less than mode. That is the kind of a distribution. We are saying for left, the tail is towards the left. So our mean is around here, and mode is the highest. Median is indeed in the middle. So mean is less than median is less than mode. An example is when we talk about the distribution of ages at retirement. The distribution of ages at retirement might be left skewed because a few people retire early. In other words, you'll find a few young people are retiring, and whereas the majority of the people retiring are always aged or the elderly. And so you'll find the distribution of these ages is left skewed, with the mean pulled down, and with a longer tail moving towards the left, so that you have a lefty skewed distribution. What about when we say right skewed distribution? The tail on the right side is longer than on the left side, and we shall have positive skewedness. So here you'll find your mean, the mean and the mode is up there. So your mean is greater than your mode, or mean is greater than median is greater than mode in simple terms. And this distribution can be seen in the distribution of income. When we have, for example, a few people in a city who own the income of that city you'll find that if we talk about the distribution, uh, the mean of the income is going to be high because you have a few people owning the biggest share of the income in the city, whereas the other hustlers are very many but earning less. So this kind of distribution is seen in income distribution where you have a few people significantly earning higher than the majority. So in general, skewness helps us to understand the direction in which the bulk of the data points are concentrated and how outliers on one side of the distribution might affect the measures like the mean. We took an example where we have ages of people retiring, and we have maybe people retiring about 35, 40, 45, and we have 70 and 100. You will see that 70 and 100 are outliers because they are far away from the general average. Because if I even add these three, cannot be equal to, in other words, their sum is less than this. And therefore, if we are taking the average of these values, the average will be affected heavily by these bigger values, and the mean will shift to the right so that it becomes a right skewed, um, a right, I mean, yeah, a right skewed distribution. It will be a left skewed distribution. So you'll find that because you have many people, if this is, for example, um, okay, let me maybe add to make it look sensible. This one, if it was like this would give you a right distribution. It would give you a right skewed distribution. But if it was, if we were having more, like 80, we have 90, we have 60, all these retiring, then remember they are higher than this, then the distribution would be left skewed. But if it was only this, then the distribution would be right skewed because you have a few higher and then uh, many less. So they would pull the mean to the right. They will pull the mean to the left, and then this would be this would reduce to this kind of distribution. So the formula for calculating sample skewness is n out of n minus 1, n minus 2, then sum of the data points, each data point minus the sample mean divided by the sample standard deviation cubed. So each of that you cube. If you have x1, you subtract the mean of the sample divided by the standard deviation, you cube. You will go to x2 minus the sample mean divided by s, you cube. Then you total all of them and multiply by n out of n minus 1, n minus 2. And you get the sample skewness. So where n is the number of data points, xi is the ith data point, x bar is the sample mean, s is the sample standard deviation. Then x bar, which is the mean, you can calculate it as that usual formula. Then the sample standard deviation, you can calculate it as that. Then you can multiply by this factor n out of n minus 1, n minus 2. Now the interpretation is that when you have a positive skewness, then you have a right skewed distribution. When it is negative skewness, you have a left skewed distribution. When it is zero skewness, then you have symmetrical distribution. and this would reduce to normal distribution. Measure of skewness using a coefficient of skewness. Coefficient of skewness, we have Pearson's first coefficient of skewness. This is determined by this formula, and this is always used only, and only you can determine mode. If you can't determine mode, then you resort to Pearson's second coefficient, where you are able to calculate median. So if you are able to calculate median, then you'll be able to get the second coefficient of Pearson's coefficient of skewness. Interpretation is that if the Pearson's coefficient of skewness is positive, you are talking about right skewed distribution. Is negative, then you're talking about left skewed distribution. Fisher's sample coefficient of skewness is always calculated from this, which is also obtained from the general sample skewness. So this is n minus 1, n minus 2 into I minus x bar, then divide by s, everything power 3. Then, of course, you'll sum all those values. So when the value is close to 0, then you have a symmetrical distribution reducing to normal distribution. When the positive indicates the skewness coefficient, if it is positive, it indicates the right skewed distribution. If it is negative, indicates the left skewed distribution. So we have said in summary, you use the Pearson's first coefficient if mode is known. Then the commonly method used when mode is not available, you use Pearson's second coefficient. Then Fisher's skewness, the most commonly used to measure and often implemented in statistical software, of course, to determine or to measure skewness. Now we looked at an example, and this example says extensions to an existing public building are to be carried out in a brickwork matching the original as near as possible. Sample measurements are taken of the combined lengths of 3 bricks and 3 joints as follows. So you have these data points. You are required to construct a frequency distribution table for these results and find their mean and standard deviation. Then also calculate the coefficient of skewness of the measurements. So we found out that we could maybe be required to determine the sample skewness. That's why we have a component of this x cubed, xi minus x bar cubed, and a component of xi minus x bar squared, which is on the formula for standard deviation. So first of all, you need to get the frequency by using tallies. So move, you write the smallest value and determine how many they are. Go to the next, determine how many they are until you finish all the data points. Then you get the mean. The mean will be sum of fx divided by sum of f. So you get the sum of fx values, which are there, then divided by 18, you will get the sample mean as 690.56. Then the xi minus x bar squared, you also get those values, and the total of them is this value, 4202.538. Therefore, the standard deviation of the sample would be computed from that. Now, the coefficient of skewness, obviously we already have mode because we see that the highest, the most appearing value is 695. We have our sample mean as 690, and we have the standard deviation. Therefore, we can get the coefficient of skewness basing on Pearson's first coefficient of skewness. And we are getting a negative, which indicates a left skewed distribution. Now, the next thing we have also discussed is kurtosis. Kurtosis is also a measure that it describes the shape of the distribution's tails. It tells us about the tailedness uh, and the presence of outliers in a data set. So when we talk about mesokartic, is a type of kurtosis where the distribution of the data reduces to normal distribution and kurtosis is equal to 0. So if we are using the excess kurtosis formula, it is 0, but it is always approximately 3. Then leptokartic, the kurtosis value is greater than 3, and you'll find that the peak of this distribution is sharper and higher, being typical of a distribution of stock market returns during a period of extreme volatility. In other words, when the prices go high in times of, for example, inflation, you will see graphs moving up like that. So the peaks are sharper and they are higher. So this would show you elliptocartic, kind of kurtosis. Then plateaucartic is low kurtosis, where the value is less than 3 or less than 0 when we are talking about excess kurtosis formula. And this kind of distribution is seen when we are talking about uniform distribution, where data is spread out evenly across the range. And this can be seen or observed in some factories. If you are having the processes under control, you would obviously have less defects, and therefore your products are going to be having less defects and spread evenly across the range. So if I put all these graphs on the same graph, then I will have leptocartic rising above all the normal distribution or mesocartic, and also the plateaucartic going below the mesocartic or the normal distribution kind of kurtosis. The mathematical formula for calculating kurtosis is this. So, whereby n is the number of data points, xi is the ith data point, x bar is the mean of the data, and s is the standard deviation. You can pause this video so that you can write down this kind of a formula, and then you can use it to determine kurtosis. Then you have the formula of excess kurtosis, which is kurtosis minus 3. So it tells us that excess kurtosis is greater than 0 for leptocartic distribution. Then when we have excess kurtosis equal to 0, then we are talking about what? Mesocartic, similar to normal distribution. If we have excess kurtosis less than 0, then we are talking about plateaucartic, and you have fewer extreme outliers than the normal distribution. For excess kurtosis, you have more outliers than a normal distribution. So if we have higher kurtosis, then there is a higher probability of extreme values or outliers, which can be important in risk management in fields like finance, where understanding the likelihood of extreme events is very crucial. Then lower kurtosis suggests fewer outliers and a more uniform distribution, which might be indicative of less variability or risk. So this can be looked at in the form of a scenario. In finance, the financial markets could be leptocartic in a distribution where you observe this that could be reflecting higher risk of extreme price movements. So when prices shoot high, then you'll have leptocratic distribution during those days. What about inequality control? Inequality control, the platocratic distribution might indicate a controlled process with fewer defects or outliers. Now, understanding kurtosis helps us in assessing the behavior of data points, especially in terms of likelihood and impact of outliers, which can be critical in various fields like finance, quality control, and risk assessment. Then we give another example of skewness. You have the data set of exam scores for a small group of students, and given that data sample, you can calculate what we call skewness. So you need to determine the sample mean, you need to determine the mode, the highest, the most appearing, the most appearing score is 85, and that becomes our mode. Then the standard deviation will be sum of xi minus x bar squared divided by n minus 1, everything under root. And you'll find that your standard deviation is approximately 14.38. Then Pearson's first coefficient of skewness, we shall use the one that has mode because we are able to determine mode. So we're getting the value of negative 0.77. This shows you a left skewed distribution. And this left skewed distribution is, of course, being indicated by the negative skewness. This means that the distribution has a longer or fatter tail on the left, with most scores concentrated on the higher end towards mode. So here you have such kind of a distribution, and the mean is going to be here, and the mode is going to be there. So here mean is less than mode. So that's all. Thank you so much for tuning in.